This is the second in a series of videos that I think I'm calling How I Teach Math. If that's not what I'm calling it, I should start. So I'm showing how I would develop a series of lessons, a unit that would eventually have students being able to answer questions, systems of equations, things like this, algebraically, and word problems that lead to systems of equations like that. And it's not something that's taught in one day. It's going to take a series of days. And so far, day 1 and 2 I've gone over. Day 1 is the idea of systems of equations. The idea that 3x plus 2y equals 12 could have ordered pairs that make it true, like 0, 6 or 2, 3. And just the idea that can we find two numbers that happen to make this true. Day 2 is where I introduce the idea of graphing. And just so you know, it's going to take 3 days with different levels of graphing. And the whole unit is going to take about 10 days. Now you may say, well, I don't have 10 days for this unit, so you don't have to do what I'm calling lessons 2, 3, and 4. I like the graphical thing, and I'm assuming I have time to do it. So if I have some flexibility and there's nobody giving me a schedule that I have to follow exactly, I'm going to do the graphing because it's going to help the students learn it better. A unit on graphing lines itself is like a 10-day thing, but somehow I just want to do enough of it, the relevant part that is going to help us solve our goal, which is systems of equations like this. On day 2, I stuck to equations where something like this, where one of the coefficients is 1, or 5x minus y equals 12, or the x could be with the 1, x plus 3y equals 15, negative x plus 5y equals 12, things like that. These are all, not putting them together, just questions like this. And day 2 was about graphing things like that by making a chart. I'll just pick one of them here. So the trick is that you can pick anything you want for y. So I put 0 in for y. I'm not sure what number that is, like 12 also. If I put 0 in for y, I need 12 for x. But if I put 1 in for y, I'd need I would need negative 12 for x, sorry. If I put 1 in for y, I get negative x plus 5 equals 12, or negative 7. If I put 2 in for y, I get negative 2, and so on. And then these points can be graphed, and that graph becomes a line, and that line, minus x plus 5y equals 12. The points on that line correspond to ordered pairs that satisfy the equation, and any ordered pair that satisfies the equation corresponds to a point on the line. And I just like that idea. That's plenty for day 2. So what happens on day 3? Well, day 3, I want to look at equations where neither of the coefficients are a 1 or a negative 1. And the students I would have as exercise now. Try to do it. And they're going to find that if they try to just pick whatever they want, they're going to end up with fractions. So if I put 0 in for x, that's okay. But if I put 1 in for x, I would end up with 10/3. And it would become a little hard to graph something like that. So for day 3, it's going to be equations like this, and I'm going to teach them the intercept method. Also, I'll introduce it. This is called standard form, when it's like something x plus or minus something y equals something. So the intercept method is where our chart just has 0 for x and 0 for y. So when x is 0, this becomes 3y equals 12 or y equals 4. When y is 0, it becomes x equals 6. So those 2 points, just those 2 points, 0, 4, and 6, 0, make our line. Now, if you want to avoid fractions, now there's nothing wrong with fractions, except it's sort of an added complication, but the trick is, if I make the number after the equal sign a multiple of 15 in this case, then I won't have to deal with fractions. So I can make up questions all day, 2x minus 4y equals minus 20, things like that. So by choosing this to be a multiple of both this and this, then I won't have to deal with any fractions in my intercepts. But you might also want them to have some experience. So then you purposely pick something that's not a multiple of 6. And now you're guaranteed to get some kind of fraction involved. Anyway, that's, I think, plenty for day 3. Day 4 is going to be our first introduction to systems of equations. And I like, when you make up a system of equations, if you want it to work out nicely, you can put anything you want on the left-hand side, and then you decide what the answer is going to be. So I want it to be 8, 2. 8 plus 2 is 10. 8 minus 2 is 6. There we go. I just made a system of equations that has a nice answer to it. This is a good question to give students the feel for how there's infinite answers to this question. 9 plus 1 is 10, 8 plus 2 is 10, 7 plus 3 is 10, and so on. And there's infinite answers to this question. 7 minus 1, 8 minus 2, 9 minus 3. But there's only one pair that simultaneously makes them both true. And trial and error, you can make up questions just to have them get a feel for like just what the goal of a thing like this is. The idea that there's many ordered pairs that make either equation true, but there's only one ordered pair that makes both equations true simultaneously. So maybe you make a few that have kind of fun, answers, but then we go like this. We say, well, what about let me go this way. 2x plus 3y, 2x minus 5y. Maybe I want to make up an answer. I will say I want my answer to be, maybe I want this to be an 18 here, so that when they graph, eventually they're going to do this by graphing today. So I want to make up a question that graphs nicely also by making this a multiple of 6. Now I need to pick an answer that makes this equal to 18. I don't want to pick 0, 6. If I pick x equals 1, then 2x is even. So that's the problem. Wait, sorry. If I pick an answer, I need to pick y to be an even number, because 2x is definitely going to be even. So 2, let's say. 2x plus 6. So 6, 2 is a answer that will make, this will be easy to graph, and the answer will be integers. If I do 2x minus 5, I just put 6, 2 in. I get 12 minus 10, which is 2. So that's problematic because when I graph this one, I'm going to deal with fractions. Maybe I'll go plus. 2 times 6 is 12. Plus, that's 22. So that's also problematic with the 5. I think I'm not going to use 5. Just for my instructive example, I'll go like minus 4y. I think that's got a better chance at working with this 6, 2. So I put 6 in, I get 2 times 6 is 12. Minus. This is okay. 12 minus 8 is 4. Okay. So now I've created a system of equations. Let me make that a little bit neater. 2x oh wait, sorry about that. I don't want to have 2x here. That makes it too easy. I make it 4x and let's say minus 2y. See if that's good. 4 times 6 is 24. Minus 4 is 20. That looks good. So you see, there's a lot of adjustment. If creating an example that works out nicely. And some people say, well, they need to learn that it doesn't always work out nicely. So why would I make it work out nicely? Why not just get fractions right away? Let them learn the world is a cruel place. But no, you want them to learn this. So they learn it with an example that doesn't have all these twists and complications in them. And this is a good question. And you could even give them that question to try to mess around with trial and error. And if maybe they come up with the 2-6 answer just by messing around, you have to decide sort of how long do you want to give them to just mess around with it. But at some point you say, guess what? There's a sneaky way to do this one. If I do the thing I learned in lesson number 3 and make my intercepts for the first equation when x is 0, y is 6, when y is 0, x is 9. And for this other one, when x is 0, y when x is 0, let's make sure this is, yeah, when x is 0, y is 10, and when y is 0, x is 5. Okay, so now I'm going to come over here. This is just a portion of the coordinate grid that I need. Hopefully I have enough of it. So for the first line, 0, 6, 1, 2, 3, 4, 5, 6, and 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that is our graph of the solution set of 2x plus 3y equals 18. On the other hand, 0, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 7, 8, 9, 10, and 5, 0, 1, 2, 3, 4. That's the graph of 4x plus 2y equals 20. And after they do this, you give them a chance to look at it and say, what do you notice? And someone will say, well, I noticed that they intersect somewhere. And even though I didn't draw this something went wrong because the answer that they should intersect at 2, 6, which is something went wrong. I'll have to think about it for a second. If 2, 6, I can't have 0, 6 here and it go through 2, 6. So what went wrong? This must be a problem. When I put, oh, 2, 6, that doesn't make this equal to 18. So that's really problematic. I think I meant the answer to be 6, 2. Six 2 does make this 18, but 6 2 doesn't make this 20 anymore. 6 2 makes it 24, makes it 28. 28 is okay, except it's going to give me 0, 14, which I don't want. So I'm going to make this that's a problem. Let me think for a minute what's a good way to get out of this. 2x. How about minus 4x plus 2y? That will shrink that number down. So minus 4x is minus 24, plus 4 is minus 20. Yes, this will fix my problems. That is also going to change. Wow, a lot of that didn't mean for all that to disappear. Okay, this is a better equation. This chart's not right anymore. 0 and negative 10, and 0 here, and 5. Okay, this should be better. 1, 2, 3. Still have the 5 here. But now the other point is at 0, negative 10, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so my other thing is down here now. That's negative 4x plus 2y. Equals negative 20. And we can see that they have this intersection point here. And we could ask the students, what is the significance of the intersection point, or what do you think the answer? How does this graph help you find the answer? So this line here is all the ordered pairs, the points that correspond to the ordered pairs that make the top equation true. And this other line is all the points that correspond to all the ordered pairs that make this equation true. So the place where they come together, I didn't draw it so well, but with a ruler and stuff is going to be 6, 2. And 6, 2 is the answer to the question. And now students are able to take what they learned on day 2 about graphing individual lines and applying it to these systems of equations. But as you can see, creating a systems of equations problem so that everything works out nicely is not so easy to do. Just to take you through, I'll try to make up another one. So 3x minus 5y. See, I can start with that and just say that that's 15. We know that's going to be nice all around. Now, as far as the other equation goes, I think I'm going to go with 2. This gives me a little more flexibility, I think. 2x minus 5y equals 20. So that's going to graph nicely. But now, is there a point on it that an ordered pair with integers that's not like 0, negative 10, something with a 0 in it. So it's got to be even, so I need y to be even. If I make y into 2x minus 10, I can have x equals 15. The problem with 15 is that it's kind of off the, I don't want my solution to be off the page. If I make this negative 2, then it becomes 2x plus 10. If I make it negative 2, that seems promising. Negative 2, 2x plus 10 equals 20. 2x equals 10, x equals 5. So 5, negative 2 does seem like a reasonable answer. Now I have to create a second equation that 5, negative 2 is true for. And it's not that easy to do this, because like if I make 3x, that's going to be 15. I think to keep it simple, I'm just going to go plus y. That way, 15 minus 2, now that's 13. It's going to lead me to a problem when I divide by 3 later. Fortunately, after day 4, we're going to get into how they don't know how hard it is to make up these problems, but we're going to switch to an algebraic approach because the graphical approach is just more of a way of getting a feel for what we're doing with this, and it's just useful for other things later on, systems of equations with graphing. Maybe I'm tempted. See, if I make this, you know, it is pretty hard to make up a question where everything works out so nicely. I would need this to be a multiple of both of these, and this to be a multiple of both of these, and, well, I guess I could be real sneaky, x plus y. If I make that my other equation, then I'm fine. Students won't know that I did that. Okay, actually I like that idea. That will always work. If you make your second equation x plus y or x minus y, it's going to work out okay. But sometimes you'll be able to fiddle around with putting something else here, but it's fine. They get plenty of practice graphing something that doesn't have ones in it over there. So, the first one, when x is 0, y is negative 4. When y is 0, x is 10. So I graph 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 10. And 0, negative 4. 1, 2 is down here. 1, 2, whoops, down here actually. Okay, so there's my first 2x minus 5y equals 20. And my second equation, x plus y equals 3, that's going to have just 3, 3 like that. You know, they don't need to, if they can do this first one, they do have the idea of graphing when there's numbers out here, so it's okay to make the second equation x plus y. This is really just for instructional purposes. And then those two things come together, and they do come together, especially if drawn with a ruler, 5, negative 2. So I guess what I'm saying is, for the second day, you can pick anything you want for this, as long as this is sort of a multiple of 5 and 2. And for this bottom equation, make x plus y or x minus y, because otherwise it might be hard to create a number here that satisfies all the properties, you know, makes this equation true for the solution point, and also it's easy to graph. So that's a little innovation in creating examples for this. I hadn't thought of that before making this tutorial. Okay, and now I have my fourth day. So to summarize, on the first is 4 days into this unit, the first day is the concept of 3x plus 2y equals 18 and trying to find, solution set for that. The second day is graphing stuff where there's a 1 in one of the things. The third day is graphing things like this where neither of these are 1 and using the intercept method. And the fourth day is a systems of equations and how that gets to 2 lines that intersect at one point. That should be the solution. That's it, just 3 days of graphing. I'm switching over to algebra in a minute. I foresee this whole unit taking 10 lessons. If you don't have 10 lessons, you could skip 2, 3, and 4. I just think that it's really good to do 2, 3, and 4 if you have the option for. So you can see how much time you have. It's up to you. But if I had total flexibility and wanted my students to learn as much as possible, I would do these days 2, 3, and 4. Okay, that's good for the second